In a separate video about projectile motion equations, I derived the relation that the height of a projectile, or the maximum height that the projectile reaches, divided by the range the projectile travels, is equal to tangent theta divided by 4, where theta is the angle above horizontal the projectile was initially fired at. In this video, we are going to gain some intuition about why this is true, and we're going to do that graphically and kind of geometrically through the looking at the trajectory of the projectile on a graph. So if we graph the trajectory of this projectile, we have that the y position on the y-axis and the x position on the x-axis, the projectile is going to follow a parabolic path and reach some range r. So this is the maximum range of the projectile. Now, in the middle of its trajectory, it's going to reach a height h, and this occurs at r over 2 because this path is parabolic, and so it is symmetric about its vertex, or the highest point, meaning that this is half the distance of its total range when it reaches its maximum height. Now, to gain some more intuition about this, let's explore what happens to the trajectory of a projectile launched without the influence of gravity. So this can be like in deep space, far away from any stars or planets or anything with mass, so there's no gravitational force on it. And since there's no force on it, that means there's no acceleration. And if there's no acceleration and no force, according to Newton's first law, it travels at a constant speed in a constant direction, meaning that it'll just go in a straight line. So if we graph that, it will look something like this. Okay, so now let's call the original projectile 1 here. So this is projectile 1, and it travels under the influence of gravity. Projectile 2 here travels without the influence of gravity. Now let's find a way to describe the path of projectile 2. So y2. We know that the angle that the projectile was fired at is equal to theta. And theta is equal to the arctangent of Vy over Vx. In this case, Vy and Vx are constant since there's no gravity. Or it would also be V0y over V0x, but this doesn't matter again since there's no acceleration. So both these values remain constant throughout its motion. Now this means that tangent theta is equal to Vy over Vx. Now, if we draw the vectors for those in here, we see that Vy, that's a bad line. So we see that Vy and Vx represented by these two vectors. So this is Vy, Vy, and this is Vx. We see that this is just the slope of the line. So because Vy is the rise and Vx is the run, or change in y over change in x. So Vy over Vx here. Oh, let me redraw this. So Vy over Vx is equal to the slope. So we have y2, since this is just a line, a linear line starting at 0. Y2 is equal to tangent theta, the slope, times x. Now, let's find two differences in height. Now, the difference in height here, let's call that y1, and the difference in height here is called that y2. So these are the differences in height between the height of a projectile without gravity and the height of a projectile with gravity. Now, we can find an equation for the difference in height with respect to time, or as a function of time. So the difference in height is equal to y2 minus y1, right? Now, y2 is equal to v0y times time. the height of this is equal to v0y times time, and y1 is equal to v0y times time minus 1/2 gt squared. So this is with respect to time, not with respect to the range, or x. Now we know, based on these two, that the difference in height is going to be equal to v0y times time minus v0y times time minus 1/2 gt squared, which is equal to just 1/2 gt squared. An important thing we can notice from this is that change in y here, or the difference in height, is so first of all, it's equal to 1/2 gt squared, but if you look at it, change in y is proportional to time squared. And now since the x velocity is constant, we know that the x position for both of these is going to be equal to v0x times time. So that means the x position is proportional to time. And so since y position, change in y here, the difference in height is proportional to time squared, and x is proportional to time, we have that the difference in height is proportional to x squared. So let's first find y2 here, change in y2, or the height, difference in height 2. So difference in change in y2, or height, difference in height 2, is equal to y2 at r minus y1 at r. So this isn't times r, this is as a function of r, or as a function of x when x equals r. Let me erase this. So y2 of r is equal to tangent theta times r, and y1 of r is equal to 0. As we can see, when it travels r, its height is 0. So that means that this difference in y2 is equal to tangent theta times r, because this term is just 0, so it just doesn't factor into it. Now we know that this difference in height is proportional to x squared. Now since its highest point here, r over 2, is half of the distance to r, that means that change in y here, since difference in height is proportional to x squared, since it's half the distance to r, this is 1/4. So that means difference in height at position 1 is equal to 1/4 of difference in height at position 2, which means that this is equal to 1/4 of, this should be 1/4 of tangent theta times r. Now, let's find the total height here, or the value of y2 when its x position is r over 2. So that's going to be in blue, this total height in blue. We have y2 of r over 2 is equal to tangent theta times r over 2. So it's just tangent theta r divided by 2 times r divided by 2. This means that this h here, the maximum height a projectile reaches, h, is equal to the total height, y2, minus the difference in height. So at position 1, or at this position, So that means that the height of a projectile at its maximum is equal to tangent theta times r over 2 minus tangent theta times r over 4, which we have found right here. And so this is just equal to tangent theta times r over 2. Over 4. And now if we move the r to the other side here, we have h over r is equal to tangent theta over 4, as we have found up here. So this proves that this is true graphically. And what this tells us is that if we look at the height divided by r over 2, so that's the ratio of the height to the distance, horizontal distance that is traveled by the time it reaches that height. A projectile will reach its maximum height when it's traveled a distance of r over 2, and this relationship is equal to tangent theta over 2. That means that the maximum height a projectile reaches under the influence of gravity is going to be exactly half of the height it would have traveled if there was no gravity and it travels the same x distance. Additionally, the two relationships we found here are very important. So the relationship that the difference in height is proportional to the distance traveled squared, and the difference in height is proportional to the time squared. These are very important relationships that you should remember, because gravity here acts with time squared. So this distance between these two heights increases as a square of its x position and as a square of time. And so this hopefully can help you gain a bit of intuition about why projectile motion follows the path that it does and why the relationships between height and range are true.